Hello, and welcome to the AI Research Roundup. I'm your host, Alex, and on this podcast, we dive into the latest developments in artificial intelligence research. Today, we're looking at a paper called VSLAM-LAB, a comprehensive framework for visual SLAM methods and datasets. Visual SLAM research, which is about mapping and localization using visual input, often faces challenges like scattered tools and inconsistent testing. This paper introduces VSLAM-LAB, a new unified framework. Its goal is to really streamline how researchers develop, test, and deploy these VSLAM systems, making the whole process simpler and more standardized. Okay, so to show how this VSLAM-LAB framework actually works in practice, the paper includes some benchmarks. Figure 1 here gives us a good look at that. It uses these radar plots to compare 4 different VSLAM methods: Mass3R-SLAM, Droid-SLAM, DPVO, and Orb-SLAM-2, across sequences with varying difficulty levels, labeled easy, medium, difficult, and extreme. Each corner of a plot represents a different test sequence, and the colored lines show how each method performed, with a smaller shape generally indicating better accuracy, specifically lower absolute trajectory error. This lets us visually compare their strengths and weaknesses in different conditions, all standardized thanks to the framework. Now, those benchmarks we just saw, well, they rely on a wide variety of test data, and that's where Table 2 comes in. It shows the extensive list of datasets that VSLAM-LAB actually supports right out of the box. You can see they span quite a few years, from 2012 up to more recent ones. It includes well-known ones like KITTI and TUM-RGBD, but also many others, both real-world data, shown in the white columns, and synthetic data in the gray ones. Having all these diverse datasets integrated really makes running those kinds of comparative tests much easier. So now that we know the data VSLAM-LAB handles from Table 2, what about the actual SLAM algorithms it integrates? Well, Table I here gives us that list. It shows the different visual SLAM methods, like Orb, SLAM2, Droid SLAM, and Mass3R SLAM, which we saw benchmarked earlier, alongside some others. It also includes a few multi-view reconstruction methods, highlighted in gray there. These are mostly focused on monocular cameras. Having this range of methods built in, spanning from 2016 to 2025, is really key to making those comparisons easy. So we've seen the datasets and the SLAM methods that VSLAM-LAB integrates. Figure 2 now shows us how the framework uses these to set up specific benchmark configurations. It groups various sequences, like the ones listed in Table 2, into 4 categories based on difficulty: easy, medium, difficult, and extreme. For each category, it shows example images from the sequences, the camera trajectories estimated by different SLAM methods, and importantly, these box plots at the bottom. These plots show the absolute trajectory error, or ATE, giving us a clear picture of how consistently each method performs across multiple runs on these different challenges. And those box plots in Figure 2 really drive home how VSLAM-LAB helps compare performance rigorously. So, wrapping up, the key thing here is that VSLAM-LAB offers this unified comprehensive framework. It makes benchmarking visual SLAM algorithms much more straightforward and reliable by integrating so many datasets and methods. This is really valuable for the AI community, helping us accelerate progress in robotic vision and spatial understanding. Well, that's our time for today. Thanks for listening to the AI Research Roundup. I'm Alex.